has been long last. That's been waiting. Before we do, do you have anything you want to look at from the problem sets? Either one or two. Some people have a book for this course. Was it in the bookstore or?
I called one afternoon. I think they had 3, and somebody bought mine. Like I got
So you go in and buy it online?
What was everybody else?
Mine came in like 2 days.
Did they say why it wasn't available?
I asked them if they was getting any more, and nobody could tell me anything. So.
You ordered from the county website or what do you want?
Half got billed.
Half? Okay. Did you get it for half?
What's that?
How much was it?
Mine was like 140.
Mine was 1/3.
And the notes are $6? Buy 20 copies of the notes. Keep them on different days or something. That might work. So I still, not enough people have books, so I still can't look at problems from the book. A few of these problems. Maybe I can, if I can explain the problem well enough. Here's a neat problem. It's just a mathematical problem. It's not really so much physics. All right, from chapter 1, that problem number 17, I'm going to read that out loud. It says, at the time of this book's printing, the United States national debt was about $8 trillion. If payments were made at the rate of $1,000 per second, how many years would it take to pay off the debt, assuming no interest were charged? We're going to start off the day with a happy note. How many years would it take to pay off the national debt at the rate of $1,000 per second? Well, what do you even take a year? What do you think before we get started? How many years would it take to pay off $8 trillion debt? Trillion. Well, 8 million years? Well, at $1,000 a second. We're going to pay it off at $1,000 a second. $8 million years is too long. So, what do you think? Not even a year, maybe? 100 years? 100 years. Okay, good. We got the whole range. Let's take a look at it. We have $8 trillion, so the debt is times 10 to the 12. The rate that we're going to pay it off with is $1,000 per second. So we could say if we were to pay off at that rate for times a certain amount of time, that eventually would equal the total value of the debt. So we could say that the debt should equal the rate times time. So the time will equal the debt divided by the rate. It's by algebra. And so we would say that would be $8 trillion divided by 10 to the 3 dollars per second. So that would be 8 billion seconds. So we want that in years, so we're going to convert that to years. So we're going to multiply this by 1 year. How many seconds are there in a year? Approximately. This is just a, what was it? Very good. Pi times 10 to the 7. Seconds per year. Yeah, 1 year per pi times 10 to the 7 seconds. So that will give us time in years. So we have 8 times 10 to the 9 divided by pi times 10 to the 7. In the previous book's printing, it was only $6 trillion. So I would just say 6 divided by pi was 2. But now it's 8, so 2.55. That's 2.55 times 10 to the 9 divided by 10 to the 7 is 10 to the 2. So that's 255 years. Which is a little bit longer than the United States has been in existence. So we could say we were founded in 1776. So it's been 232 years in the United States. On the average, I guess. Yeah. That's just the debt, so that's not just paying the interest on the debt. Of course, this is not economics class, so that's all I'll say about that. Except there's a part B to this. It goes like this. A dollar bill is about 15.5 centimeters long, and $8 trillion bills are laid end to end around the Earth's equator. How many times would they encircle the planet? Or would it even encircle the planet? So if we took $8 trillion bills, laid them end to end around the Earth's equator. This one's kind of rounded off on the edges. Now we look at this and lay these end to end around the Earth's equator. Do you think it would actually go around the Earth? And if it did go around the Earth, would it actually make it around again? Or more than once or twice? What do you think? Just, it's okay to guess. That's what we're just doing. We're just guessing. You think it'd make it around the Earth? Probably would make it around the Earth. There'd be a lot of paper. Probably would make it around the Earth. More than once?
About more than 10 times.
More than 10 times? Is that what you're saying, Dean?
Oh, definitely.
Yeah. Okay. All right, let's say more than 10 times. Here's a dollar bill. The length of the dollar bill is 15.5 centimeters. So let's write that in meters. 155 meters. we're going to extend that around the Earth. We're going to extend these dollar bills around the Earth like that. If we had $8 trillion bills, the total length we're going to be talking about would be the number of dollar bills times the length per dollar bill. So the total length would be 8 trillion times 0.155 meters. And that comes out to 1.24 times 10 to the 12 meters. The circumference of the Earth around the equator, that was one of those fun facts we had in this chapter as well. Do you remember what that number was? Almost exactly. Around the equator of the Earth was 40 million meters. 40 million meters. So the circumference of the Earth is 40 million meters, or about 4 times 10 to the 7 meters. By definition, basically, from 1799. So if we were to put this length in terms of circumference, then we would say that the total length is some number, let's get a different number, times the circumference around the Earth. That number will equal the total length divided by one length around the Earth. So that would be 1.24 10 to the 12 divided by 4 times 10 to the 7. Which would be a nice round number, 31,000. Times. So, if we were to take the United States national debt, placed it dollar bill by dollar bill around the Earth's equator, it would go 1 time around the Earth, 2 times around the Earth, 3, 4, 5, 6, 7, 8, 31,000 times around the Earth.
No wows?
Wow.
Wow.
Wow. I say it a little louder. Wow. 31,000 times around the Earth. I don't know why more political candidates don't talk about that. We laid the national debt around the equator, it would go 31,000 times. Maybe that'd be just too overwhelming. When you start throwing numbers out like that, you say, oh yeah. My numbers say only 29,000. So. The Earth's circumference is 40 million meters. If I did that in terms of miles, it is about 25,000 miles. The distance to the moon is 250,000 miles. So the distance to the moon is 10 times the Earth's equator. So if I divide this by 10, then, and we were to lay the national debt towards the moon, then it would make it to the moon, at least that distance, 3,100 times. And if it went to the moon and back again, then that would be more than 1,500 times to the moon and back again. Just to put it into perspective. Like I said, we start off the day with a feel-good problem. Just print more money. This would actually be a feel-good problem. Here's problem number 28 from chapter 1 as well. Again, it's just a guesstimate type problem. Suppose Bill Gates offered to give you $1 billion. Already this is sounding good. Bill Gates is going to give you $1 billion if you can finish counting it using only $1 bills. Should you accept his offer? Explain your answer. We'll assume that you can count one bill every second, and note that you need at least 8 hours a day for sleeping and eating. All right? So you can have $1 billion if you can count it. How long would it take you to count your money? So sum $1 billion. So a billion is 10 to the 9. And we can say that the rate that we can count is $1 per second. So again, we would say that this sum would equal the rate times time. So our time to count this money would equal the total sum divided by the rate. 10 to the $9 divided by $1 per second. Would be 10 billion seconds, or a billion seconds. 10 to the 9 seconds. And again, if we converted that to years, say there's 1 year, and pi times 10 to the 7 seconds.
So at 30-something years, if you didn't sleep or eat,
Can I do that right? You say 32 years? Or would it be longer? Yeah, that's about right.
Well, but that's without.
that's without sleeping or
8 hours.
Okay. So that's if you never slept. And if you're just counting bills in your sleep, you probably could do. But. So if you never slept, 32 years, but if you did sleep, then 50% more than that time, because 8 hours in a day, that's 1/3 of the day. So we'd have to multiply this by, so our true time would be this time multiplied by 1.5, so that'd be 48 years. I'd be afraid that after 47 years, I'd say that's 900 million, 92, and no. Oh, goof up after 47 years and have to start over again. You don't get it right. So if you worked 48 years in your life, that might be worth $1 billion.
Do you actually do it, or you have to wait, because it's already.
You have to wait, I think. You have to count it first.
Unless you already have it,
So at least your errors would be counted.
You just take out a long bit off here and you're gonna count.
Anything from chapter 2? You have a chance to look at any of those problems?
Number 7.
Number 7? Okay. A lot of these problems, like number 7, will be a whole lot easier after today. We have to introduce those 5
That's the
equations.
equations.
Yeah, we have to introduce those 5 equations that I've
What,
got.
was it in the book or?
It's in the book, it's in the notes book, we haven't covered that material yet.
Well, we'll knock up to 6. Are we able to do that one?
We're going to do number 6 based on the definition of acceleration. But again, it would be easier if we had this equation. Number 6, an electron starting from rest and moving with constant acceleration travels 2 centimeters in 5 milliseconds. What's the magnitude of this acceleration? Yeah, let's wait.
I think that's a good.
Yeah, let's wait. In fact, let's just go right into the lecture. We need all the lines up. Last time we introduced the 3 major kinematic variables. We introduced what was called displacement, which was equal to the final position of something minus the initial position, basically in straight line motion as the crow flies from one position to another. And based on that definition, we define what we call velocity, average velocity, as being the displacement per time. So whatever displacement you have between 2 positions, divided by the time it took you to cover that, was called the average velocity. And in the limits that your time interval approached 0 at any particular moment, then we could define what was called the instantaneous velocity, the velocity at a certain moment, a certain point. And after that, we defined what was called acceleration. And we said acceleration was the change in velocity over the change in time. So the acceleration would be in some time interval, your velocity at the end of that time interval minus your velocity at the beginning, divided by the time it took you to cover that interval. Change in velocity over change in time. That would be average acceleration. And instantaneous acceleration would be the limit in which that time interval approached 0. So you would get that change in velocity and change in time at a very specific moment. But we said, for our purposes, we're just going to deal with constant acceleration. So for our purposes, average acceleration will be the same as instantaneous acceleration because we're not going to change it. It's going to be a constant acceleration situation. And we said that intuitively, we know what acceleration is when you feel a force. You know, when you actually have something and you feel a force occurring, then you know you're being accelerated. And I think that was pretty much it. Kind of defined those variables, and we talked about it a little bit. And so, today we want to come up with 5 kinematic equations. Kinematics being the study of motion. We're going to come up with 5 equations that use basically 5 variables. And with these equations, you'll be able to describe motion in our everyday world. These are 5 equations that will come up again and again and again throughout your physics career, throughout your engineering career. So this is one of the most important sections we're going to cover, because you're going to see this again and again, and that's why I would suggest that you memorize these equations. And you can put them on your card, that's fine, but I would also suggest that you just go ahead and memorize these. So the first one, if we start off and say our initial time, ti is 0, we're just going to say, let's start our clock at initial time of 0, just to simplify things. And we'll say our final time is just t. So we'll start at 0, and we'll just start the clock, and any final time is just going to be time t. We're going to call our initial velocity v naught, just to use different nomenclature. So instead of v sub I, it's just going to be v sub 0, v naught. And we'll call our final time just v, velocity. So our final velocity is just v. So with these definitions, we can say that the acceleration is the change in velocity over the change in time. So the acceleration is our final velocity minus our initial velocity, v naught, over the change in time, which would be t minus 0. And so we could write the acceleration like this. Change in velocity over change in time. Rearranging this using algebra, multiplying both sides by t, and adding a v naught to both sides, we get this. Velocity equals initial velocity plus the acceleration times time. Velocity equals initial velocity plus the acceleration times time. For example, if I were moving at 10 meters per second, and I were to increase my speed at the acceleration of 2 meters per second, so that after one more second I'm moving at 12 meters per second. After another second I'm moving at 14 meters per second, then 16, then 18, then 20. Let's say I did that for 5 seconds. Then I would say my final velocity was my initial velocity, which was 10, plus my acceleration, which was 2 meters per second, times time, which is 5 seconds. So my final velocity would be 10 plus 2 times 5, or 10, 20 meters per second. Makes sense. Your final velocity equals your initial velocity, whatever that is, plus your acceleration times time. We call this kinematic equation number 1. As I call this kinematic equation number 1. In this equation, there are 4 variables. There is final velocity, initial velocity, acceleration, and time. I promised you 5 variables, but there's 4 of them right there. If we assume the acceleration is constant and in our everyday world, near the surface of the Earth, that's a good assumption. So we're going to assume the acceleration is constant, and we're going to say that our initial time is 0. Then under those conditions, I can say that my average velocity is equal to my final velocity plus my initial velocity divided by 2. If I use that previous example, if I started at 10 meters per second, and I were to accelerate at a constant rate for 5 seconds, and my final velocity was 20 meters per second, I could say that over that time interval, my average velocity was 10 plus 20 divided by 2, which would be 30 divided by 2, or 15 meters per second. So I would say that if I were to look at that interval, I was moving at an average speed, an average velocity of 15 meters per second. So this makes intuitive sense. If you're only dealing with constant acceleration, and that's all we're going to deal with, then you can take your initial and final velocities, divide by 2 to get your average velocity. And we also said that average velocity was equal to our displacement for time, so our displacement is equal to our average velocity times time. Displacement being delta x. So, plugging in the definition of average velocity into this displacement equation, I have displacement equals average velocity, 1/2 final plus initial velocity times time. That is kinematic equation number 2. Basically says displacement equals average velocity times time. In this equation, we have 4 kinematic variables. We have displacement, delta x, that's understood to be your final minus your initial position, but that's one variable, delta x. We have final velocity, we have initial velocity, and we have time. Comparing this to equation number 1, we're missing one of our variables. We're missing acceleration. Acceleration was the 5th variable. What I will learn is that if I read a problem and acceleration, for instance, is never mentioned in the problem, not given, not asked for, then the equation I want to use will be this one. Okay? Because it has all the variables that are either given or asked for. And that will be something that you're going to apply to all these equations we're going to introduce today. If something's never mentioned and never asked for, those 5 kinematic variables, that will help you determine which formula, which equation to use in the problem. If we take equation 2, and we just introduced, displacement equals average velocity times time, and if I rearrange equation number 1 in terms of t, so equation number 1 was final velocity equals initial velocity plus acceleration times time. I'm going to rearrange that in terms of time. So time will equal final velocity minus initial velocity divided by acceleration. I'm going to plug that into equation number 2 for t. So I get this nice expression. Displacement equals 1/2 final plus initial velocity times final minus initial velocity over acceleration. Why? Why not? I got rid of time. What is the quantity of when you have something plus something times something minus something? What do you call that? What does that end up being? When you have, like in this case, b plus b naught times b minus b naught, what happens when you multiply that out? It's going to be b squared minus b naught squared. It's called the difference of squares. Called the difference of squares. So I can write those 2 parentheses like this. B squared minus B naught squared divided by 2 times acceleration. Let's multiply both sides by 2a and add a B naught squared to both sides. With that algebra, we end up with this. Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement, delta x. This is kinematic equation number 3, at least by my definition. In this equation, we have 4 variables. We have final velocity, initial velocity, acceleration, and displacement. You're missing a 5th variable, which happens to be time. If you read a problem and time is never mentioned, never asked for, never given, then this would be a good place to start. In other words, in the problem, you probably would be given 3 variables in the problem and asked for a 4th one. If you were, say, given initial velocity, acceleration, and displacement in the problem, they might ask you for what was the, did I say initial velocity, or
So
what was the final velocity, for instance. In other words, in the problem, you probably would be given 3 variables and ask for the 4th variable. That would help you define the equation that you need to use. The 3 that were given, the 4th that's asked for, solve for the unknown. So you're going to read a word problem and look for what's given and solve for the unknown. If we take equation number 2 and we substitute in final velocity from equation number 1, we recall the equation number 1, final velocity equals initial velocity plus acceleration times time. We get this: displacement equals 1/2 initial velocity plus acceleration times time plus initial velocity, all that in parentheses, times time. So I'm going to have a 2v naught plus at in the parentheses there. When I multiply all that through, I'll get this. Displacement delta x is equal to initial velocity times time plus 1/2 acceleration times time squared. This is kinematic equation number 4. In this equation, we have 4 variables: displacement, initial velocity, time, and acceleration. We are missing final velocity. We are missing final velocity. If I were to read a problem and final velocity wasn't given, never asked for, and not given, then this might be the equation I want to use. Or conversely, if I were to read a problem and 3 variables were given, and the 4th one asked for, those 3 that were given and the 4th one being asked for would help me define the 4 variables I need to have in my equation in order to solve it. A lot of kinematics might just stop here. They'll say, well, that's all you need, it's just 4 equations. But you know, it's kind of nice to be complete and actually have 5 equations for 5 unknowns. We have 5 variables that we call unknowns here. And so there really is a 5th equation that would have 4 of the variables and miss the 5th variable. But before I show you that, let's take a look at this last equation, this equation number 4. Recall that displacement is your final position minus your initial position. If we think of our final position as being a variable x, our initial position as being a constant, it's going to be someplace where we're going to start. We're going to call it x naught. So that's just a constant. I can rewrite the last equation in terms of position like this. My position is equal to my initial position plus my initial velocity times time plus 1/2 my acceleration times time squared. And before I do the next step, I would notice that my position is equal to 3 terms: initial position plus velocity times time, initial velocity times time, plus 1/2 acceleration times time squared. Let's do a little dimensional analysis of this. If I look at those 3 things that I'm adding, the dimensions of position x naught is going to be meters. The dimensions of initial velocity times time is going to be meters per second times seconds, which will be meters. And the dimensions of 1/2 acceleration times time squared will be meters. Because acceleration is going to be meters per second squared times second squared will give me meters. So really, dimensionally, I'm adding 3 things that are all meters. If you ever get confused in an equation, I can't remember whether it was t squared or t, you can think about the dimensional analysis of it. It should be velocity times time, so I end up with meters. It should be acceleration times time squared, so I end up with meters. All right, let's start with this equation. Let's take the derivative of it, because we can. We know that if we take the derivative of position x with respect to time, that's the same as the definition of instantaneous velocity. Right? Velocity was dx over dt. So let's do that. Let's say velocity is dx over dt, and I'm going to take the derivative of x in this form. Now, if I take the derivative of all that with respect to t, x naught being a constant, v naught and acceleration are constants for that matter as well, because we're taking the derivative with respect to time. So the first term, x naught, is going to be 0. The second term, derivative of v naught times time, will just give me v naught. The last term, derivative of 1/2 at squared. I'm going to use the power rule, drop the square down from the t. So I'm going to have just acceleration times time. So I end up with this. Velocity equals initial velocity plus acceleration times time. If I take the derivative of kinematic equation number 4, I end up with kinematic equation number 1. By definition. Velocity equals initial velocity plus acceleration times time. Let's not stop there. Let's go ahead and take the derivative of the velocity with respect to time and see what we get. So I'm going to take this final equation we have here and take the derivative of that. Now we know that dv over dt, the derivative of the velocity with respect to time, by definition should be acceleration. So we'll say acceleration is the derivative of the velocity with respect to time. We're going to do d dt of v naught plus at, v naught being a constant, acceleration being a constant, our variable is time. So when I take the derivative of v naught, I'm going to end up with 0. And the derivative of the second term, we'll get rid of the t, and I'll simply say that acceleration is equal to acceleration. Neat. So it kind of checks out with calculus. As promised, we have a fifth equation. Let's look at it this way. If I start from equation number 2, displacement equals average velocity times time, and I substitute in for our initial velocity from equation number 1. Since v equals v naught plus at, v naught should equal v minus at. I'm going to substitute that in. So now I have this. Displacement equals 1/2. Final velocity plus final velocity minus acceleration times time times time. I'm going to multiply all that through. I end up with this. Displacement equals final velocity times time minus 1/2 acceleration times time squared. This is the least intuitive of the kinematic equation. That's probably why it's neglected the most. But it's still a usable kinematic equation. And in this equation, there are 4 variables. There's displacement delta x, final velocity v, time t, and acceleration, and we're missing initial velocity. So if I have a particular word problem that I read, and initial velocity is never given, never asked for, then this would be a good place to start with the equation I need. So we have 5 kinematic equations. In terms of total displacement, delta x, which is equal to our final position minus our initial position, initial velocity v naught, final velocity v, time t. We have kinematic equation number 1. Velocity equals initial velocity plus acceleration times time. In In this equation, of the 5 kinematic variables we're interested in, this one has 4 of them. If I read a problem and 3 of those variables are given, the 4th one being asked for, I can solve for the unknown using this equation. Or conversely, the displacement delta x is never mentioned, never asked for, I can use this equation to solve that problem. Kinematic equation number 2, displacement equals average velocity times time. We're going to write average velocity as the final plus initial divided by 2 times time. In this equation, we have 4 variables. We're missing acceleration. If I have a problem and acceleration is never given, never asked for, great equation to use. Kinematic equation number 3. Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement delta x. In this equation, 4 variables are a part of that equation. Time is never mentioned. If I read a problem and time is never given, never asked for, then I want to use this equation. Kinematic equation number 4, displacement equals initial velocity times time plus 1/2 acceleration times time squared. This has 4 variables in it, missing final velocity. So if I were given 3 of those circled variables and asked for the 4th one, then I might want to use this equation. And the final one, go backwards. The final one has the displacement, final velocity time, and acceleration, missing initial velocity. That helps define what we can use. There's your 5 kinematic equations. Like I said, you're best off memorizing them now. And I won't tell you to memorize too many things. But if you memorize these, it'll really help you keep you in good stead. And you never know, there might be an extra credit problem in Physics 2, which might assume that you know these equations, right? And Physics 3 as well. So every once in a while, and if I say it's extra credit, that means, I can ask anything, and even though, you may not have been forewarned, one of the things I might assume in an extra credit problem is that you know the kinematic equations. So let's try this out in the problem. Here's problem number 27 in your book, or at least it should be around there somewhere. A jet plane lands with a velocity of 100 meters per second and can accelerate to a maximum rate, at a maximum rate of -5 meters per second squared as it comes to rest. The question is, the first question is, when the incident touches the runway, what is the minimum time needed before it stops? Alright, so a jet plane hits the runway with a velocity of 100 meters per second, accelerates at a rate of -5 meters per second squared as it comes to rest. What is the time needed before it stops? Let's identify the variables that are given in this problem. What are we given? Initial velocity, which happens to be what? 100 meters per second, correct. Initial velocity is what you have at the beginning of the problem, at the beginning of your time interval. So we're going to start with initial velocity of 100 meters per second. We're also given acceleration as a -5 meters per second squared. So acceleration could be negative. And when you put it into your equation, then you're going to have to put it in as a negative value. So we have initial velocity, acceleration. What else is given or asked for? Time is asked for. So time is going to be part of our equation as well, because we want to be able to solve for unknown. And the third variable that's given is final velocity, which happens to be 0. Not given to us explicitly, is it? It's implied, as we came to a stop. So our final velocity was 0. They're not always going to say final velocity is 0, right? So that might be implied there. But there we have it. Initial velocity 100, final velocity 0, acceleration minus 5, time is asked for. With those variables given and time asked for, we want to use kinematic equation number 1. We identify the 4 variables. They're either given or asked for. So we use kinematic equation number 1, solve for the unknown. Initial velocity, or final velocity being 0. So time will equal a negative initial velocity over acceleration, which will be at negative 100 meters per second over negative 5 meters per second squared. Negative over negative gives us positive. So it's going to take us 20 seconds to stop. If you come up with a negative time, then you might assume that you did something wrong somewhere. Either that, or else you've discovered something very important. I'll go back in time, which you'd have to let me in on it. Try to make money on it. Part B, can this plane land at a small airport where the runway is 0.8 kilometers long? Can this plane land at a small airport where the runway is 0.8 kilometers long? 0.8 kilometers would be how many meters? 800 meters. All right? So, how can I answer this question? Would be able to land at a runway that is 800 meters long. Right, we were doing
Found time, initial velocity, final velocity.
exactly. We found time.
Choose one. As long as it's built in.
Exactly. Everything you said, Brad, is exactly what I want to say. We know 3 variables already. We know initial and final velocity, and we know acceleration. And we also found the 4th variable. We found time. So we know 4 variables. What we don't know is displacement. Even though we were given a distance, 800 meters, is that not displacement? It's a displacement of some sort, but it's not the displacement that we wish to find, because we want to find out what's the displacement for our aircraft, all right, and then compare it to this. So, as Brad said, since we actually know 4 variables, we have our choice. In that 5 kinematic equations, the displacement comes up 4 times. So we have our choice of 4 different equations that we could use for this. I don't know which one I used. Oh, okay. I selected equation number 3, possibly because I'm assuming that we didn't know part A. I mean, we didn't come up with the answer from part A, so I just assumed that if we had read this problem initially, with what was given initially, then I would handle it that way. It probably wasn't a bad idea, just in case I made a mistake in part A and got the time wrong. Final velocity 0, solve this for displacement. Displacement equals negative initial velocity squared over 2 times acceleration. That'll be a negative 100 squared over 2 times a negative 5. Gives me 1,000 meters. So, can I land this airplane at this airport? No. I need 1,000 meters to stop, and I only have 800 meters at the airport. So as I'm coming down the line, land, I make this quick calculation in my head. One of the many things that pilots have to do. You know, they say you can read altimeter, you know, and you look at the signs on the right and left, and can you calculate kinematic equations in your head? That's things you have to do if you're a pilot. Are there any pilots in here? So you have to kind of do this on the fly, so to speak. And you calculate that you need 1,000 meters of land, so you pull up and you go to the next airport. Let's try another problem. This is problem number 19 in your book. Jules Verne proposed in 1865 to send men to the moon by firing a space capsule from a 220-meter long cannon with a final velocity of 10.97 kilometers per second. What would have been the unrealistically large acceleration experienced by space travelers during this launch? Prepare your answer with the free fall acceleration of 9.8 meters per second squared. Jules Verne was a great author. He came up with 20,000 Leagues Under the Sea, Captain Nemo. So he kind of proposed, wearing oxygen gear in order to go underneath the ocean, and then he thought about going into space and going to the moon in 1865, long before it ever became a reality. So his idea was that we'd launch these space capsules in a 220-meter long cannon and reach an escape velocity of 10.97 kilometers per second. Actually, to escape the Earth and actually have enough momentum to make it to the moon. So, what is given in this problem? What do we know in this problem? What variables? Final velocity. We want to find acceleration. Someone said displacement.
Initial velocity.
And initial velocity, correct. So our initial velocity is 0. We start from rest. Our final velocity is 10.97 kilometers per second. Our displacement is 220 meters. We're going to try to do all this. We're going to accelerate within 220 meters of the cannon. And the thing we want to know is acceleration. So there we have it. We know initial velocity, final velocity, displacement delta x. We want to know acceleration. Time was never given, never asked for. So we look at our equations and we find out which equation doesn't have time. And that's equation number 3. Or conversely, which equation has the 3 variables that were given and the 4th variable that was asked for, and that would be equation number 3. So final velocity squared equals initial velocity squared plus 2 times acceleration delta x. Initial velocity is 0, so let's just get rid of that. And solve this for acceleration. So we have acceleration equals final velocity squared over 2 times displacement. That would be 10.97 times 10 to the 3 meters per second squared over 2 times 220 meters. Gives us an acceleration of 2.735 times 10 to the 5 meters per second squared. So that's 273,500 meters per second squared. Gravity, which we'll introduce in a few minutes, gravity is an acceleration of 9.8 meters per second squared. So what we call 1G is 9.8 meters per second squared. That's what we experience in our everyday lives. So if I were to put this in terms of G's, I would divide this by 9.8 and say that these astronauts will experience 2.79 times 10 to the 4 G's, or 27,900 G's. Does anyone happen to know what our astronauts experience on a flight-by-flight basis? Any idea? Yeah, exactly, 6 to 9 G's. Astronauts, normally they'll pass out for a little while. So as the rocket's going up, you're experiencing 6 or 7 G's, you might pass out for a few seconds under 6 or 7 G's. 27,900 G's is not going to do it. If you want your astronauts to survive on their trip to the moon, you don't want to do it. Incidentally, in Jules Verne's book, Going to the Moon, something like that, Trip to the Moon or something, they did have a dog on the ship, and the dog died on takeoff, probably from the 27,900 feet. So they did a proper burial, and they sent the dog out into space. And unfortunately, the dog had, once they were out in space, the dog had the same velocity as the spacecraft. So as the spacecraft's traveling the moon, the dog traveled with the spacecraft. And so the whole way that they're traveling to the moon, they're looking out the window, and there's a rover, looking right back at them. Here's Colonel Staff, who, are you ready for the pop quiz? This is actually a picture of Colonel Staff as he decelerated from, I think, 600 miles per hour down to 0 in a matter of about a quarter mile when they were doing all these test factor 50s. So they wanted to see what human beings could withstand. And I think when it was calculated what kind of G force he went through, I think it was 20 G's or 22 G's or something like that. And all his blood vessels in his eyes popped, and he couldn't see for a couple of days. And I don't think anybody else tried to beat this record. Okay, I'm going to stop the PowerPoint there. Let's take a look at these problems that we did not do at the beginning of class. Let's start with problem number 7. Problem number 7 says a rocket initially at rest is fired vertically with an upward acceleration of 10 meters per second squared at an altitude of 0.5 kilometers, the engine of the rocket cuts off. It's not a good one to start off with. What is the minimum altitude it achieves? All right, well, let's do it. The reason why it's not a good one to start off with is because it's actually 2 problems in one. It's actually, we're going to have to apply the kinematics twice on this problem. And also, we have not introduced gravity yet. So let's hang on to this for a few more seconds. Let's see if we can. All right, let's look at number 6 right above it. An electron starting from rest and moving with constant acceleration travels 2 centimeters in 5 milliseconds. What's the magnitude of the acceleration? All right, so we have an electron, negatively charged particle, starting from rest, so that tells me initial velocity is 0. So let's go ahead and write that down. And moving with constant acceleration, okay, well, that's good. We're going to always assume that that's the case. Travels 2 centimeters, so that tells me displacement. 2 centimeters would be 0.02 meters. In 5 milliseconds, so that is, time is 5 milliseconds. 5 times 10 minus 3 seconds. Already we're given 3 variables. The question is, what is the magnitude of the acceleration? There we go. 4 variables, 3 of them given, 1 of them asked for. So if I look at this, with these 3 variables given, 1 asked for, which kinematic equation would I use? Number 4? Yeah, if I definitely want to use just these 4 variables, I would use kinematic equation number 4. So kinematic equation number 4 looks like this. Displacement equals initial velocity times time plus 1/2 acceleration times time squared. We're kind of lucky here that our initial velocity is 0. Otherwise, we would have to use a quadratic formula to solve this. But initial velocity is 0, so that's good. Solve this for acceleration. So we'll multiply both sides by 2. Divide both sides by time squared. So acceleration will equal 2 times displacement over time squared. So that would be 2 times 0.02 meters over 5 times 10 to the minus 3 squared. I get 1,600. Meters per second squared. That's not any of my answers, but 1.6 kilometers per second squared would do the trick. So if I converted that, let's say acceleration is 1.6 kilometers per second squared. So far, so good? Take a look at number 5 right above that. An automobile traveling along a straight road increases its speed from 30 meters per second to 50 meters per second, a distance of 180 meters. If the acceleration is constant, how much time elapses while the auto moves this distance? automobile. One thing you'll learn is that my talent for drawing is well surpassed. But sometimes it really helps just to draw a stick figure or something to kind of illustrate what's going on. So in this case, we have an automobile traveling on a straight road. It says it increases its speed from 30 meters per second to 50 meters per second. So 30 meters per second is initial velocity. So let's call that initial velocity. And sometime later, we have a final velocity of 50 meters per second. We're going to do this in a distance of 180 meters, so that tells me displacement. Delta x. So delta x with 180 meters. Nice. We already got 3 variables. 3 of them already defined. How much time elapses while the auto moves this distance? And now we're asked for time. With those 3 variables in that time, I choose kinematic equation number 2. Correct. So I'm going to say that displacement equals average velocity, which I'm going to write as initial plus final divided by 2 times time. I want to find time, so let's solve this for time. Let's multiply both sides by 2. Divide both sides by velocity plus initial velocity. So time will equal 2 delta x over velocity plus initial velocity. That would be 2 times 180 over 50 plus 30, 80. That would be 360 divided by 80. That's 4.5. Seconds. What do you think? So we have 5 kinematic equations. I want to throw you one more twist on all this today, and that is we've talked about we can use these 5 kinematic equations if the acceleration is constant. And in our lives, that's a common situation. If you're near the surface of the Earth, we're under a situation, at least vertically, where we have a constant acceleration, at least for short distances. And that acceleration that we are under is called gravity. It's something you're going to measure in experiment 2 and experiment 3, by the way. No experiment today. Unless, how many people missed the first experiment? Right. If you want to make up that experiment today, then you can work together and make that up today. Get it out of the way. And get yourself started. But in the experiment 2 and 3, you're going to measure gravity. The accepted value is 9.8 meters per second squared. Down towards the center of the Earth. So, if you deal with a problem that is vertical, that is motion going vertical near the surface of the Earth, then one thing that is assumed, and it's not going to be stated explicitly in that problem, it's assumed if you're dealing with a vertical problem like that, let's assume that you're under gravity and that your acceleration is 9.8 meters per second squared down towards the center of the Earth. Now, whether you call that acceleration positive or negative depends on your choice. Right? It could be positive, it could be negative. I mean, if you were falling down towards the center of the Earth, you're increasing speed as you're falling. So you might think of that as a positive acceleration as you're falling towards the Earth. You might think of other things as well, but if you're thinking physics, which is the curse of physics, is that in weird situations you start thinking physics when you shouldn't think about physics. But if you were falling, you would say that that would be a positive acceleration towards the center of the Earth. However, if you were going up, say, or if you're throwing the ball up or something like that, you might think of that as a negative acceleration because acceleration is down towards the center of the Earth, and you're going up like this, and it's slowing you down, or slowing the ball down. So your dilemma is, when do you call acceleration positive, when do you call it negative? When you call velocity positive, when do you call velocity negative? How are you going to define positive and negative? Because you want to use these equations that you're going to know and love. So, I'm going to give you a rule of thumb. If you're dealing vertically with a known acceleration of 9.8 meters per second squared towards the center of the Earth, we call that acceleration G, acceleration of gravity. That it's a nice thing to just define whatever your initial velocity direction is, define that direction as your positive direction. Whatever your initial velocity direction is, define that direction as your positive direction. If I'm going up, I'm going to define up as positive. If I happen to be going down, I'm going to define down as positive. So, once I do that, once I either define up as positive and for that matter down as negative, or I possibly could define up as negative and down as positive. Or whatever my initial velocity direction is, I'm going to define that as positive. All other variables will be defined with whatever direction you've chosen. For instance, if I were to define my initial velocity as being positive going up, then that would automatically make acceleration of gravity what? A negative 9.8 meters per second squared. Because acceleration of gravity is always 9.8 meters per second squared down. So if I define up as positive, acceleration of gravity is negative 9.8. Conversely, if I were define down as positive, if I were moving down initially, and I would just say that that's the way I'm going, that would make the acceleration of gravity a positive 9.8 meters per second squared. That would make any displacement in that direction positive, acceleration positive. All your variables in that direction are positive, all your variables in the opposite direction are negative. Make sense? Let's try it out. Before we do number 7, I can still say, look at number 12. So the rock is thrown downward from an unknown height above the ground with an initial speed of 10 meters per second. It strikes the ground 3 seconds later. Determine the initial height of the rock above the ground. You're going to throw a rock down, and your initial speed is 10 meters per second. So we're going to call that initial velocity. Would I call that a positive or negative 10 meters per second? Positive, because I'm going to call my initial velocity direction positive. So I'm going to define that as a positive 10 meters per second. And in doing so, I'm also going to define that direction as positive. So down is positive. It says it strikes the ground 3 seconds later. So my time is 3 seconds. What else do I know? All right, I got a couple answers there. Let's think about these. Final velocity, ultimately it's going to hit the ground and stop, right? Hang on to that. Acceleration is 9.8 meters per second squared. Positive or negative? Positive, because I defined down as positive.
I got a question. You said the ball is thrown, then I say it's dropped. So you wouldn't have to take account.
Right. I mean, what we're going to do is that we're going to say we're going to start our time as soon as the ball leaves our hands.
So we're not throwing it, we're actually dropping it.
No, we're throwing it, but the constant acceleration, this will answer the other question as well, whether the final velocity is zero or not. When we use these 5 beautiful equations, we can only use them when the object in question is under constant acceleration. Right? The only way this would be a constant acceleration is when the ball leaves my hand. Because when the ball's still in my hand, I'm applying force on
I
it.
see what you're saying.
And I'm changing the acceleration.
Acceleration stays the same.
Right.
Okay.
So only way I can call it, use a kinematic equation, is when the ball leaves my hand. And for that matter, why can't I say that the final velocity is 0? Because when it hits the ground, what happens?
Negative acceleration.
There's a negative acceleration on it by the ground. There's a force on it by the ground. So all I can talk about is the motion of this ball when it leaves my hand and to the very moment right before it hits the ground. Because a moment later, it's under a force, it's under a non-constant acceleration. So, same.
This is sort of like the limit of thing. Like we're not really focusing on the point, we're focusing on the point like right before it. It's not
Right,
like a limit.
right. Yeah, you take a limit, arbitrarily as close as you wish
Right.
before it contacts the ground. Once it contacts the ground, all bets are off. I can't use kinematic equations on that. Right? So I can't say that the final velocity is 0. Actually, the final velocity is some great speed right before it hits the ground. Right? We can calculate what that is. So these are actually the variables I want to use right here. Initial velocity 10 meters per second, acceleration 9.8 meters per second squared, time 3 seconds, and what were we asking for? No, the initial height of the rock above the ground. So we want to find displacement, and I'm going to call that displacement delta y in this case, since we're vertical. We want to find out what delta y is. So I have 4 variables. I have 3 given, 1 asked for. Initial velocity, acceleration time, and displacement. I identify a kinematic formula for that, which is the 4th one. So I'm going to say, in this case, displacement y equals initial velocity times time plus 1/2 acceleration times time squared. I'm going to write it as the full equation in its full form, its correct form. I already have the variables defined perfectly. So let's solve this for displacement. That is initial velocity, which is 10, times time, which is 3, plus 1/2 acceleration, which is 9.8, times time, 3, squared. 30 plus 9.8 times 4.5. 74.1? 74.1 meters. Yes.
So if you can bring something against gravity, you use.
The value would be 9.8, and your major task at that point will be to decide whether it's negative or positive. And like I said, we just go with the direction that you initially throw it. Call that positive. I mean, you could go with any direction as long as you're consistent with all your variables. You'll define all your variables with that direction. So you could always say, if you wish, always say that up is positive, in which case your acceleration of gravity would always be a negative 9.8. But then you'd have to be careful. If I were to say up is positive, let's try it. Let's define this problem with up as positive, or it might be confusing, after I've already defined this. If I were to say up was positive, I would have to define my initial velocity as a negative 10, in the opposite direction. And I would define my acceleration as negative 9.8. Fortunately, those two negatives would have worked together on this, and my answer would have been a negative 74.1, which, if I had defined up as positive, that meant my displacement was negative 74.1. Correct answer. So you can't go wrong as long as you're consistent with whatever you define, but I'm just saying, just go ahead and define your initial velocity direction as your positive direction. If you drop the ball and it comes back up, like bouncing, then what do? If you were to drop the ball and it hit the floor and came back up, you can only use these Kinematic equations for the time to where right before it hit the floor and the time right after it left the floor and came back up. You can't use it for the whole problem. At least not in terms of, you could figure out, average velocity for the whole thing, but that's the only thing you could do. Dan?
But we can figure out the force that's acted upon the board.
Which is something we'll do later on.
Sorry.
But as far as just pure kinematic motion, we can deal with forces and change the momentum later on. But these equations, we can only talk about intervals where we have constant acceleration. All right, so let's look at this number 7 that I've been skipping. Number 7, a rocket initially at rest is fired vertically with an upward acceleration of 10 meters per second squared. At an altitude of 0.5 kilometers, the engine of the rocket cuts off. What is the maximum altitude it achieves? We're going to fire a rocket, initially at rest, with an upward acceleration of 10 meters per second squared. All right? So, we have one problem that's dealing like that. What do we know? The initial velocity is 0. Final velocity, we don't know. But we do know the acceleration. The acceleration would be 10 meters per second squared. 10.
What about the gravity coming down on it?
What about that?
Wouldn't it be like 0.2? Wouldn't it be 10 minus 9.8?
I don't know. What
Is that why you'd have to use two problems? You can only do this till it goes to, it's only
Well, see,
50 kilometers, and then you gotta stop at 50 kilometers, calculate how far it's gonna go with gravity going down. So half of it goes with that, with the acceleration of 10 meters. The other half problem goes
Why?
with 9.8.
Why do I ignore gravity on this first part of this problem?
Because it has to have constant
Because
acceleration.
we're told we have 10 meters per second squared. All things considered.
Oh, so that the 10 is already calculated gravity already.
Exactly. It's saying it's moving at an acceleration of 10 meters per second squared, gravity, whatever else considered.
Okay, I see what you're saying.
All right?
So it's not talking about the force exerted, it's talking about the overall acceleration period.
Right.
Okay.
So the first problem is just dealing with that. So our acceleration is 10. So the first part of the problem is it's almost like gravity wasn't there, because we already know all of our variables. Displacement is 0.5 kilometers, so we'll just go 500 meters. So we have three variables. And we want to find what is the maximum altitude achieved. So we already know it goes, in the first part of the problem, we already know it goes 500 meters. Right? But what we could do is use this information to help us for information for the second part of the problem. And for the second part of the problem, what does it look like? So here's situation one here. The second part, it continues to go up until it reaches a maximum height. All right? What do I know about the second part of the problem?
Can't you find the
You
initial
want to find
velocity?
the initial velocity.
You find the velocity of the first.
Very good. I can use the first one to find the final velocity, which will actually be the initial velocity for the second one. Right? All right, so let's do that. Let's find the final velocity here. All right? If I know acceleration, displacement, initial velocity, those three things with the fourth one unknown, I use Kinematic Equation number 3. So I'll say that final velocity squared equals initial velocity squared plus 2 times acceleration, displacement, delta y in this case. Let's solve this for final velocity. So final velocity would be the square root of all this stuff, which will be 0 squared plus 2 times 10 times 500. So it'll be the square root of 10,000, which is 100, right? Yeah, 100. So our final velocity for the first leg is 100 meters per second, and that happens to be our initial velocity for the second leg when the engines are turned off. So at that moment, we have initial velocity of 100 meters per second. Someone said we also know the acceleration for that second leg. What is the acceleration for the second leg?
Negative 9.
Negative 9.8. Very good. The acceleration for the second leg is a negative 9.8. Negative because we're calling our up direction as positive and gravity's towards the center of the Earth is in the opposite direction.
We know the final velocity.
What is the final velocity?
0.
0, because we're going to go as high as we can go and go no further. So at that moment, we momentarily are stationary. So we know our final velocity is 0. Great. We've got 3 kinematic variables. So we can solve for, let's call it delta y2. So if we solve that, we have initial velocity, final velocity, acceleration, delta y2. You use Kinematic Equation 3 again. So I would say that, at least for the second leg, final velocity squared equals initial velocity squared plus 2 times acceleration, delta y2. And when I'm working these problems, I would always just write out the full algebraic equation first before I proceed, because that you just get in the right habit of writing the right equation and then proceed from that point, and you make a lot less errors. Final velocity is 0. We want this to solve this for delta y2, so delta y2 is going to equal a negative initial velocity squared over 2 times acceleration. So that's going to be a negative 100 squared over 2 times a negative 9.8. And that comes out to 510 meters. So we had this delta y, which is 500 meters. This delta y is 510 meters. So ultimately, we go up to a height of 1 kilometer, 1,010 meters. Our total, I should call that delta y1, but our total distance, our total height, delta y from delta y2, 500, 510, 1,010 meters. Or 1 kilometer. This is one of those problems, you know, it's 2 problems in one, and you say, great, you know. Dr. Golben didn't give us enough problems, and here it's like a bonus problem. It's 2 in 1. Fantastic. Very important. So try your hand. You've got, well, we got this weekend. I know the Australian Open is this weekend. So in between watching all that tennis, see if you can work out some of these problems. And we'll see you next